Hello and welcome to the first section of the Analog Electronics course. So as we develop our understanding through this course, what we're going to be doing is really moving from a world of ideal circuits into a more realistic understanding of what these circuits can do. We're going to be thinking about things like noise, and we're going to be understanding what makes a good circuit as opposed to a bad circuit, for example. And also we're going to focus perhaps on two example applications. The first one is really relevant to what's known nowadays as the Internet of Things, the use of sensors to measure things in the real world and control them through computer systems. So we're going to be looking at the instrumentation amplifier that would interface between the sensor and our digital controller. And we'll also be looking at applications like power amplifiers, for example in music. How do we amplify music without distorting it and getting and distracting from the music itself? How do we generate a very good power amplifier circuit that can give us a really good amplification of our music signals, for example? I've provided here three examples of books which more than cover the topics that we will cover in this course on analog electronics. But to be honest, the course is self-contained, so you'll be provided with all the material that you need, so you don't need to buy these. They are just here in case of reference, or that you want to borrow them from the university library. Of course, digital electronics is nowadays really the dominant form of electronics. But actually, when you think about it, it builds on initially, for example, analog devices like transistors, and it creates them puts them together to create the digital devices that we use. So it makes logic gates, makes registers, logic blocks. That builds into a CPU, for example, and then that leads obviously to the highly advanced computers that we use in everyday life now. But of course, underpinning that is the actual analog devices, which are the foundation really of all of this type of electronics. So at the very least, if you want to understand digital circuits, you need to have some basic understanding of the analog devices which are inherently used to make up the digital circuits at the very fundamental level. Another important consideration is that many of our systems nowadays, such as your phone, it's about a digital system interacting with a human. And of course humans are fundamentally analog. We don't work on a digital basis, we work really in an analog way. And so therefore all of these digital systems need to have an analog component to interact with the real world. So in the case of a phone, obviously it's the sound signal or the vision of the screen, but in many cases, for example, we'll be building systems that use a sensor or to record some values from the real world that are then processed by analog circuitry before being fed into a digital computer that will then make decisions, but then has to send those decisions back out to the real world through power circuits and actuators. So we always see in many cases a combination of analog and digital electronics, and we need both of those really to do many of the exciting things that we do in electronics nowadays. For example, robotics is inherently a technology that depends on both digital and analog electronics, and that's just of course one of many examples. So both technologies are really important for electronic engineers now. Now in this slide, what I'm showing is some financial figures about the importance of electronics technology. So we can see over the last few years how the value of electronics has risen enormously in the global economy. It's now one of the dominant forces that's driving the economy in almost every country. And the point I'm trying to make here is that this is not just about digital electronics. What we can see in the market is that both digital and analog are growing very fast. And what that means is that there's lots of job opportunities in both fields, and more importantly in being able to connect between analog and between digital and analog, as we see many of the consumer technologies, the high value technologies, are actually a combination of both of these kinds of electronics. Okay, we've spoken really about the motivation as to why it's still important, or it's even growing in importance, to study analog electronics. So let's move on now and start to think about some of the technology that we're going to be developing over the next few weeks. Now, in many cases in electronics, we're using electronics to represent information, to process information. That's inherently what we do in a computer, for example. And just as we are probably pretty familiar now with that we represent information in a digital world by a stream of bits. So on the right hand side of this slide we can see a series of digital bits that could be, for example, inside a CPU unit. There are also analog ways to represent information as well, and the traditional method, in fact, actually was to think about techniques like amplitude modulation, where we might modulate a carrier wave according to the information that we wanted to encode in it, or frequency modulation, where we kept the amplitude of the wave the same but we changed the frequency. Now, both of these methods are commonly used in many radios, for example, although of course now we're seeing digital radio where we've actually got a digital signal that's being transmitted and superimposed on the carrier wave as well. So all of these are just examples of the ways that we can represent information. And what we're going to see really is how we move from one of these different forms of information, how we can move information between the analog and the digital world without any loss. So we don't want to lose information, we don't want to scramble the information, and we don't want to distort the information. And for that we're going to need some good circuit design to make sure that that doesn't happen. In general, we can represent information in both analog and digital forms. And in this slide I've tried to explain how we can represent the same information in these different ways. So I've divided the page up from left to right, ranging from purely analog representation of time to a discrete or digital representation. And then going up and down on the page, I've represented the signal between an analog signal and a discrete digital signal. And these four quadrants give us a way to think about the ways that we can represent information in different ways. So starting at the top left, in a fully analog representation, we have a traditional signal that varies both in time and amplitude. So that could be a sound wave, for example. As I go across the page, I can convert that by discretizing it, changing the levels of the signal into a number of discrete levels. That's a common way that I might convert an analog signal into digital through using a digital to analog converter circuit, and we'll see more about those later in the course. As I go down the page, I can convert that information into a more completely digital form through the use of a synchronized signal. So that could be, as we do in a digital circuit, we have a clock signal that synchronizes everything. And that's the typical method that we would use in digital electronics. And then going to the final quadrant on the bottom left corner, that is a representation of what's called an asynchronous digital circuit, where there's no clock signal, but I might use the time signal as part of the information representation. So this could be something like a PWM output that we use to control in digital control, for example. So the four quadrants represent the range of ways that I can think about the same information, and what we're often going to be doing in this course is transforming signals and information between these different quadrants by using these specialized circuits that we're going to describe as we get through the course. We've discussed how information can be transformed from the analog to the digital world and back again. But now let's have a look at how we might do that from a system perspective. So this slide shows really a representation of the idea of an analog system. So an analog system might sit between a real-world device like a keyboard or a guitar or any kind of real-world object, and it might move that information or that signal into the digital world. And generally that middle section, the analog domain, is going to contain a number of different things. It's going to usually contain some kind of amplification, some kind of signal processing or filtering. We might want to remove unnecessary background noise, for example. And then generally we're going to do some kind of conversion to a digital signal. And then often we come back the other way, bringing information back into the analog world through an analog conversion and then amplification and back into our real world object. So this analog system, the analog domain, typically contains these very important functions, and we're going to be looking at all of those as we go through the module and understanding how to build a technology that can deliver what we want in that analog domain. Now, consider, for example, some kind of sensor system. So the sensor will record a value of something. Often we then need to amplify it, for example. We might put it through an analog to digital converter, and then we'll send it into our microcontroller or our CPU or some kind of digital processor. But at the heart of this really is the sensor. That's the first stage and very important. And if we think about the signal that we might get, say, from a typical sensor, it might just be a few millivolts, and it may vary over a period of time. We may have issues that we have to deal with, like long-term drift. The sensor may change its values over time, or may record different values on different days, for example. We might got interference from very common sources, like the 50 Hz power signal that we use in our fluorescent lights, for example, often creates interference with the signal. Or we may have more general noise from other things in the background. And all of this will combine to present the signal that we actually receive at the amplifier. So the right hand graph really there shows the kind of thing that we may actually see as we bring that signal into our analog system. And that's quite different from the original sensor signal. So we need to understand how to process that signal to get it back really to the original value of the sensor system. Now when we start to process that signal, what we'll find is typically is that we need to amplify it. And obviously for that we use a circuit component that you're all familiar with, an amplifier. Could be an op-amp, for example. Now of course what we'll find though that it's more complicated. There's different kinds of amplifiers, and we need to be able to choose the right one for the right kind of application. In many cases what we're interested in is the so-called signal amplifier. This will be something that reproduces a sensor signal, for example, with very low distortion, and may, for example, in a portable device, may be very important that it's very efficient in terms of power. So many of the applications that we use in everyday life, like a phone, for example, we don't want that phone to last all day long. So we want any amplification that it does to be done in a very energy efficient way. But there are other applications where we're really interested in creating a very powerful amplifier. So for example, this could be a music player. If we want to amplify the signals coming off an MP3 player, then what we're interested really is creating a very powerful amplifier that can amplify the signal very rapidly to provide some kind of high level power amplification. And that's a different kind of circuit probably than a signal amplifier that we might use with a sensor. More generally, we might classify amplifier types into perhaps 4 different categories, and we use these different ones for different kinds of applications. So probably what you're most familiar with here is category 2, the voltage amplifier. A simple op-amp might be one of these, for example, or a simple amplifier circuit where you use the voltage in the signal controls the amplification. But there are also other types as well, so-called current amplifiers, and more complicated types like transconductance amplifiers and transresistance amplifiers. We're going to touch on all of those in the course, but we'll be focused really on those that we need for the particular applications that we've got in mind. Now, I've already spoken quite a lot about the importance of changing signals from the analog world into the digital world. And we're typically going to do that with specialized circuits. An analog to digital conversion circuit, which takes the analog signal, turns it into a stream of bits. And then if we want to bring it back out again, then we're going to use another specialized circuit called a digital to analog converter. Now, both these circuits we're going to study in detail in this course because they play an absolutely crucial part in all of these kind of modern complicated electronic systems. And we'll be looking at the types of circuits that you might select for those for different kinds of applications. And as I've said already, we're going to be using some examples as we go through the course to understand what makes a good and a bad circuit. So in this graph, for example, I've shown an Internet of Things system that measures air pollution. So this is a big problem around the world. Cars produce a lot of pollution, unfortunately, at the moment, and that pollution needs to be measured. So you typically have a system where you have a sensor that might measure, for example, the nitrous oxide which is emitted by the car, and that will then feed into a microcontroller through an ADC that then has some kind of communications type system. So these are very important class of problems that we can directly address through the use of analog electronics. And what we'll see in those systems is the kind of signals and circuits that we've already talked about today. So we're going to be seeing complicated signals where we'll have noise, interference. In there will be our real signal that we're trying to work with, but we need to have all of those electronic components to enable us to strip out all of these unwanted effects. So I hope this section has given you an overview really of the course that we're going to be studying over the next few weeks. Analog electronics plays an incredibly important part of modern life. It's an area that is growing just as fast as digital electronics, and of course it's the crucial interface between digital electronics and the real world. So I hope I've convinced you of the importance of studying analog electronics and given you some flavour of the different things that we're going to be looking at over the next few weeks.